how much CO2 is too much? Well, the first question is, why are we concerned particular about CO2 rather than, say, methane, which is another greenhouse gas? Well, the answer to that is that CO2, as you know, kind of accumulates in the biosphere, whereas methane is a transient greenhouse gas that breaks down in about a decade. So the long-term climate change that we're worried about is mostly that driven by CO2. So I've seen sort of evolution of people's thinking on this question over the decades, actually. So sort of in the 80s and 90s, the people were talking in terms of stabilizing atmospheric CO2 concentration. So trying to come up with how much CO2 we can release that would make the concentration rise and then plateau at some level, like 750 parts per million, or 550 is doubling the pre-anthropogenic value of about 280, or 450 or something like that. So when you release CO2 to the atmosphere, as you now know, some of it dissolves in the ocean and some of it goes into the land biosphere, and only some of it continues to reside in the atmosphere. And so there were efforts to use carbon cycle models to figure out, given some set of emissions, what the concentration would be. And then figuring out how to exactly follow along one of these stabilization scenarios was another sort of inverse problem, like the borehole temperatures, where you had to use the model to sort of go backwards from the effect back to the cause. So this was a little dodgy because slight changes in the trajectory could have very large changes in what they said we could release this year or next year. So it was kind of a confusing situation. Of course, we can't see or taste CO2. The thing that really bothers us is the temperature. So a natural evolution of this was to graduate to temperature targets. So what does it take to keep Earth's temperature at some given level, and sort of a benchmark? So the European Union has taken 2 degrees C as a sort of a target temperature change. Now, 2 degrees C is warmer than the Earth has been in millions of years. It's warmer than it has been the whole time that civilized humanity has existed, with agriculture and all that sort of thing. So a more conservative temperature target is advocated by Jim Hansen. 1 degree C is sort of within the natural range of climate variability over the last throughout the period of time covered by the ice cores, actually the last hundreds of thousands of years. And if we could keep Earth to within 1 degree C, it decreases the odds of provoking some kind of a slow Earth system feedback, like the collapse of ice sheets, the release of extra carbon from melting permafrost, and methane hydrates in the oceans, changes in ocean chemistry, all kinds of sort of scary things that are outside what's happened in the last 500,000 years. We could avoid if we could keep the temperature to 1 degree C or less. So in thinking about those temperature targets, it turns out that a lot of the complexity of the carbon cycle goes away. And that's illustrated by these sort of schematic cases of releasing a slug of carbon, either doing it very quickly all at once, or doing it slowly but for a longer time, so that the total amount of carbon is released is the same in either case. So there's a fast slug of carbon released and a slow slug of carbon released. So if you release the carbon quickly, that reaches the CO2 peak by the time at the end of the slug, and then it sort of slowly drifts down as it's being neutralized by the oceans and whatnot. If you release it more slowly, it reaches a peak that's later and probably a lesser peak, because as you've been releasing it, it has had time to dissolve in the oceans. But the temperature response goes as the CO2, but there's a lag time for the change in the temperature of about 1,000 years, because you have to heat up the ocean. So it turns out that the temperature sort of rises up to a plateau, and then it basically just stays there. As far as we're concerned, it stays there forever. But the crucial part to this is that the plateau temperature that it reaches for these two scenarios is about the same in either case. It turns out that the higher CO2 is counterbalanced by the fact that it started dropping by the time the Earth's temperature is catching up. And so the time dependence of the absorption of CO2 is kind of compensated for by the time dependence of the warming. What this means, what it boils down to, is that in terms of the temperature that you're going to reach, it doesn't matter if you release it quickly or slowly. You're going to reach the same temperature in either case. You'll reach it more quickly or more slowly depending on how quickly you release it. But it's a much simpler picture now, because we can just draw a one-to-one relationship between the amount of carbon ever burned and the temperature that the Earth will reach. So it turns out that about 1,000 gigatons of carbon would take the Earth about to this 2 degrees C threshold. 500 gigatons of carbon would take it about to 1 degree C. So for comparison, we've already burned about 300 gigatons of fossil fuels and cut down about 200 gigatons of trees. So we're kind of in the 1 degree C area already, and we're about halfway toward this 2 degree C mark. So what would it look like to actually try to cut emissions and stick to one of these, say, 1,000 gigatons of carbon as a target? Well, here is a plot of emissions of carbon per year, and business as usual is this line here. It's growing at a rate of 3% per year. That's the trajectory that we continue to be on. And the total amount ever burned goes as the area under this curve. So let's say that in 2010, we had decided, instead of growing at 3% per year, we would cut emissions by about 2% per year. That way, the emission flux would sort of drop in this gradual sort of way, and the total area under this curve would come in at about 1,000 gigatons of carbon. If we wait longer, we have to cut more quickly in order for the total area under the curve to stay under 1,000 gigatons. So here's a plot of the percent per year cuts that would be required in order to keep to 1,000 gigatons of carbon for the total slug as a function of the year that they start. So starting in 2010, cuts of about 2% per year would have done it. 2020, we would have to cut by 4% per year. 2030, about 10% per year. And pretty soon, by around 2040 or so, basically would have to cut cold turkey in order to keep under 1,000 gigatons of carbon. So it's kind of like, you know, you're in the Army and your sergeant has caught you doing something wrong. He says, drop and give me 20 push-ups. Or if you don't want to do them today, you can do them tomorrow, but you got to do 40. Or you can do them this weekend, but you got to do 100. So what are you going to do? It's much easier, cheaper to convert our energy infrastructure at a slow rate of a few percent per year, because that's kind of the rate at which power plants become obsolete and need to be replaced anyway. Whereas if you wait till the end, you got to basically build everything all from scratch all at once. It's a much bigger and much more expensive proposition. Winston Churchill once said of the Americans that we can be counted on to do the right thing after we've exhausted all the alternatives. So what are the alternatives to actually cutting our CO2 emissions? Generally, they're called geoengineering, which is the idea that we're now powerful enough that we can actually engineer the planet in some way. So there are different strategies that are all called geoengineering. They're very different and have different degrees of possibility of actually working. So the one way that could actually work to solve the climate problem and is my hope for the best outcome for the future is to actually eventually scrub CO2 from the atmosphere. This could be done. CO2 reacts with a base to make bicarbonate. We saw this using carbonate ion as a base in the seawater chemistry. This is the buffer mechanism why seawater can hold more CO2 than it would if it didn't have that chemistry. Well, it can be used in an industrial way too, and the base that they usually talk about is called an amine, but it functions in the same way. So you run the CO2 through a solution of this, and it turns into bicarbonate, and then you have to get the CO2 back off again and do something with it. And so this is how they scrub CO2 from the air in submarines, and it's also how they scrub sulfur dioxide from exhaust from coal power plants. So it's not a novel sort of a process. Once you've captured the CO2, then you've got to figure out what to do with it. And the word they use for this is CO2 sequestration. And there are two basic options on land and in the ocean. On land, there are deposits like layers of sandstone, which is coarse enough grains that there's fluid in between that can sort of flow around, and deep enough that the water inside there is salty. So they call these saline aquifers. Since the water is salty, nobody wants it, might as well put some CO2 in it. It turns out that there is capacity for thousands of gigatons of carbon in these sorts of deposits in the earth. They're not evenly spread out around the earth. We have lots of them in the United States. There are no such deposits in Japan, for example. But the CO2 at this pressure is actually a liquid rather than a gas, and it eventually reacts with the CaO component of rocks that are down there. So that's the Urey reaction again. We pump the CO2 down there, and it can react with igneous rocks to sort of permanently neutralize it. The other option that people talk about is to inject it in the ocean. So here's a ship and a pipe and a bubbler, and you bubble some CO2 out, and it floats up. It would be liquid in that case, but it would float. Well, actually, it depends on the depth in the ocean. At some depth, the CO2 is more compressible than water, so it would actually sink. But either way, it would eventually dissolve in the water. And once that happens, the CO2 dissolving in the deep ocean, it would exchange with the atmosphere on a time scale of about 1,000 years, just the same as if we had put it in the atmosphere. It would take 1,000 years to equilibrate with the ocean, then you'd have this long tail. You put it in the ocean, it would take 1,000 years to equilibrate with the atmosphere. So this process would eliminate the peak, but it wouldn't eliminate the long tail. It would only be sort of a partial solution to what to do with the CO2. Another idea that you hear about, which I am personally not a believer in, is to fertilize the ocean. So it's found that in large sections of the surface ocean, the phytoplankton, their growth is limited by, it needs trace amounts of iron, Fe. And so there are people who think about putting iron in the ocean, making the phytoplankton grow, and then these dead phytoplankton will sink in the ocean and sort of pull CO2 out of the surface ocean. And this is a very strong lever because you only need 1 atom of iron for maybe 20,000 atoms of CO2. So it seems like a very powerful technique. The problem is that the CO2 in the atmosphere only exchanges with that from the ocean in, like we've said, about 1,000 years. So if you could fertilize the ocean for 1,000 years, you would start to get somewhere. But in simulations of what happens if you just fertilize for in one spot in the ocean for a few decades, it's found that the impact on the CO2 in the atmosphere is very, very small. And in fact, if you put iron in one spot in the ocean models, you make lots of production in that spot, growth of phytoplankton, but there are other nutrients like nitrogen and phosphorus in seawater that limit how much phytoplankton can grow. And so by making one spot that's very productive, you make a donut of areas around it that are less productive, and so it sort of compensates. So the impact on atmospheric CO2, according to the models, is low. And if it were actually done, you wouldn't really be able to measure how much you are changing the CO2 concentration of the atmosphere. So if you're looking to buy carbon offsets, the right to emit carbon by investing some money, and someone wants to sell you carbon offsets by grinding up old cars and putting them in the ocean, I would advise you to put your money elsewhere. The other strategy for engineering the climate, broadly speaking, is called solar radiation management. So the idea is that aerosols scatter sunlight. Now, aerosols released to the troposphere, like from power plants, don't last very long. There's rain in the lower atmosphere, and the rain tends to scrub those particles out on a time scale of a week or two, something like that. Whereas if you can put the sulfate aerosols up into the stratosphere, it never rains from up there. And so you have to wait for those little droplets to slowly settle through the air, and they last for a year or several years. So it's been calculated that something like 1/10 of the amount of sulfate aerosols that we now produce as a byproduct of coal production, if we just put those in the stratosphere, that would be enough to make a big change in Earth's climate. And it's been tested, in fact, in a natural way by volcanic eruptions. The last really large volcanic eruption was Mount Pinatubo in the Philippines in 1991. It was big enough that it actually put aerosols into the stratosphere, and it led to a measurable cooling for about 1.5 years. And so we know this would work. The near-term problem with this is that basically what we're doing is we're substituting, we've got this stronger infrared energy coming down from all the CO2 in the atmosphere, and we're compensating for that by making the solar flux less intense by putting these aerosols there. Well, the difference between sunlight coming down and infrared light coming down is that the sunlight makes it all the way to the ground. And when it does that, it provokes water that's at the ground to evaporate, to carry away that heat in the form of latent heat. Infrared coming down from the greenhouse gases and the clouds and things like that tends to get absorbed in the atmosphere, in the boundary layer, just the bottom layers of the atmosphere, by the water vapor in the atmosphere. So when the light is absorbed by water vapor, it leads to heating as opposed to evaporation. So in the case where we have got more infrared from the greenhouse gas pollution and we're substituting less solar by putting the aerosols there, we're getting less evaporation overall. So this is expected, it would be a more arid planet. And the Pinatubo years were in fact more arid than normal. On a longer time scale, the problem with solar radiation management as a fix for climate change is the long lifetime of atmospheric CO2 in the atmosphere. So we could use solar radiation management if the climate got out of control and we wanted to ramp it down for a few decades, put up with the dryness while we scrub CO2 from the atmosphere. But it's wrong to call the solar radiation management any kind of a fix for global warming, because we'd be leaving the planet to our descendants on life support. And if they failed to pay their climate bill, they would get clobbered with all the climate change that we've built in to the atmosphere with the higher CO2 concentration. So at best, it's a Band-Aid, and it couldn't be considered as a real fix.